This is going to be a long video. I'm going to take the time to work through the whole review sheet since we had so many out today who were testing and our test is tomorrow. So I'm going to start with the beginning and work all the way through. Watch, fast forward, do whatever you need to get what you need. Looking at just the properties of different types of bonds, identifying whether each characteristic is ionic or covalent. So in class, if you go way back, we've done labs and different things to help us to determine that. So if it dissolves in water, that means it's soluble. That means it's an electrolyte. So it would be ionic. If it conducts electricity in solution, that's another key thing for an electrolyte. It is also ionic. Electrons are shared in bonds. So shared, that's where we get that term co for covalent. So it would be covalent. KBr, potassium is a metal and bromine is a non-metal. So when I have a non-metal and a metal paired together, that means they transferred electrons. That is ionic. Electronegativity difference is 1.7 or greater. That should say equal to 1.7 or greater. That is the definition for ionic. I'm going to go back to number 4. Another thing you could look to check the difference here is you could look at the difference in electronegativity. Bromine has an electronegativity of 2.8 for bromine, and potassium has an electronegativity of 0.8. So when you subtract those, they have an electronegativity difference of 0.0, which is greater than 1.7. Number 6. Each one of these things in this compound are all non-metals, and so that is an indicator that it is covalent. If we call the compound a molecule, that is also covalent. If you remember, we call ionic compounds formula units because they break apart. We call covalent compounds because they stay together because they're sharing electrons. So if it occurs between a cation and an anion, those words ion in there should be a clue. That is ionic. Okay. Number 9, which elements do not follow the octet rule? So if you go to your Vespers sheet, this is your Vespers sheet, down at the bottom, there's a list of the elements that are an exception. It says always 8 except. Hydrogen, because it only has 1 energy level, is okay with 2 electrons. Beryllium is satisfied with 4. Boron would be satisfied with 6. Aluminum also with 6. Phosphorus would be okay with 10 or 12. Sulfur would be okay with 10 or 12. So those are your exceptions. That's where that's coming from. So hydrogen, these are my exceptions. Hydrogen, beryllium, boron, aluminum, phosphorus, and sulfur. Those are all exceptions. Which compound exhibits the strongest intermolecular force? So we got to think of a couple of things. Here, carbon and hydrogen, when we build this molecule, is balanced. And so it is non-polar. Oh, I skipped number 10. I'll go back and do number 10 in just a second. So this one is non-polar, so it's not going to have a very strong intermolecular force. This is covalent, so it actually breaks apart into a positive potassium ion and a negative chlorine ion. So because of that, it is definitely very strong because you've got one positive molecule or one positive ion and a negative ion. And then oxygen is going to be nonpolar because it's symmetrical and it's balanced. So the strongest intermolecular force is going to be this ionic compound that breaks apart. So back to number 10. What type of bonding is found in magnesium sulfate? So this is an ionic bond because I have the magnesium ion and then I have sulfate, which is a polyatomic ion, but it is also covalent. So you have ionic between Mg and SO4. Sulfate, I think, is -2, right? These two ions, that bond is ionic, but then you also have covalent bonds within SO4. So this polyatomic ion has covalent bonds, but then you've got also ionic between the magnesium and the sulfate. Number 12, which substance with the strongest a substance with a strong intermolecular force will have a high melting point. Those attractive forces make it really hard to break them apart. And a weak intermolecular force is going to have a low melting point. Why are valence electrons shared between two atoms? If you remember the octet rule, everybody's trying to be stable and have full valence electrons. So to reach stability, full outer shell, and you could even remind yourself the octet rule is what we're trying to achieve. All right, number 14, list the electronegativity ranges for ionic, polar covalent, and nonpolar covalent. So ionic is going to be greater than or equal to 1.7. Polar covalent is 1.69 to 0.5. And non-polar covalent is going to be 0.49 all the way to 0. So all the bonds for diatomic molecules are non-polar because a number minus itself is always 0. Why is water able to be used as a universal solvent? Because of its polar qualities. It will dissolve and pull apart anything that has that's polar. Number 17, rank the following bonds from least to most polar. So there's a couple of ways of looking at this. You could actually do electronegativity differences and subtract and rank them accordingly. Or you can look at what kind of molecules they are. So the most polar is going to be our ionic. So NaCl is going to be the most polar. Then it is going to be water. And followed by, I think that's cyanide. I can't remember. Yeah, cyanide. And then last, with no polarity at all, is going to be a hydrogen molecule. Okay, so those would be our rankings. And again, you could look at your electronegativity chart and you could subtract and see what the differences are in each of those. If you were to take chlorine is 3 and sodium is 0.9. So if we were to subtract those, you're going to have 2.1 as the electronegativity difference. if you take carbon and nitrogen and their electronegativity difference is 0.5, hydrogen's with itself, so that would be an electronegativity difference of 0, and then oxygen is 3.5 and water is 2.1, and so there's an electronegativity difference of 0.4, which is exactly how we ranked it. So sodium, water, cyanide, hydrogen. Number 18 says finish the dot structure to the right. So hydrogen has, if we were to think about it, there's a dot there, right, that's being shared, and there's a dot here that's being shared with bromine. So bromine has 6 other valence electrons that should be shown. So there's our valence electrons for bromine. 9 says draw an arrow to show the direction of the partially negative side of the molecule. So how do we determine what that's going to be? We're going to go to our electronegativity chart. You can also just look at where they're located on the periodic table. Bromine is over here. It's part of the halogens. Hydrogen's way over here. So the further we go towards the noble gases, that halogen group is our strongest electronegativity. So the direction is going to be that way. If you're more visual, you could actually write the differences, 2.1 and 2.8. So bromine is my winner in that wonderful electron tug of war. All right, 20 through 27 has us naming. So we've got to go back to that flow chart, and you can remember all the rules that go along with naming. So important is identifying, is it covalent or is it ionic? And after you've decided if it's ionic or covalent, then you choose which type of naming. So here I have 2 non-metals. So because they're both nonmetals, that is ionic. Sorry, because they're 2 nonmetals, that is covalent. So this is going to be, I'm going to name the first element sulfur. And then the second element gets a prefix. 6 is hexa. And then the second word, we're going to write chlor and change the ending to IDE. We drop the end and add IDE. So sulfur hexachloride. Again, here I have 2 non-metals. So if the first one is more than 1, it gets a prefix. So this is going to be tetra nitrogen. We don't change the end of the first word. And then hexa oxide. Again, we have another non-metal and non-metal. So this is carbon monoxide. And then chromium and oxygen. I've got a metal with a non-metal, so this is going to be ionic. So here's where we've got to do the reverse crisscross. So this 3 comes up here to be a 3+. This 2 goes up here, that's a 2-. When we're naming ionic, we use the charges for the multi-oxidation numbers. So this is chromium, and we're going to write chromium with a Roman numeral 3 because it's a multi-oxidation element, and just oxide. We don't need to change the ending at all, or we don't need to add any prefixes. That's the most common mistake on this test. Then number 24, we're going from names to formulas. So I have diphosphorus, so that means phosphorus is P, 2 for di, pentabromide. Bromine is Br5. Make sure you look up the names for the symbols and that you've got those correct. Next, selenium diphenol. chloride. So because of that prefix di, I know that it is covalent, so I just have to look up the symbol for selenium. SeCl2. And then pentabromide, so that means Br5 hexafluoride, or pentabromine hexafluoride, F6 is going to be my equation for that. And then iron 3 sulfide. So I got to do a little work because I got this Roman numeral. Fe3 plus. Sulfur, if you look it up, sulfur is 2 minus, so we're going to crisscross. And I got 2 and a 3, so my formula is Fe2S3. All right. 28 asks you to draw the Lewis structures for all of the diatomic. If you remember, the diatomic elements are the ones that start with nitrogen, which is number 7, and they make a 7. And you've also got to include hydrogen. So we're going to do those. So we're going to start, I'm going to start with hydrogen, and then I will do the others. That's hydrogen. Then we're going to do nitrogen. Then oxygen. Fluorine. Chlorine. Bromine. And iodine. All right. Now, the last part says how many total valence electrons do each of the polyatomic ions have? The key thing here is that you're including the charge and the electrons that are in the charge, or in this case that you're taking away, and that you write those out. So your total electrons equal all of them that would be there had you drawn it. So for this one, for chlorine, you're going to have chlorine bringing 7 valence electrons, oxygen bringing 6, plus that negative, which means there's 1 more electron. So if I add all of these up, I have 14 valence electrons. Oxygen is going to have 6, hydrogen has 1, and that negative gives us another 1, so this is a total of 8 valence electrons. Okay, we're going to skip this one because chromium is a multi-oxidation number, and we haven't practiced that. Chlorine has 7, and I have 3 oxygens, and you must remember all 3 of them. On the quiz, a lot of you only did 1, you didn't do all 3. And I have a negative sign, so we got to make sure we include all of those. So this is 18, 19, 26. And this one's going to be a little tricky because we got that positive, right? So nitrogen has 5. I have 4 hydrogens, each with 1. And then because of this plus sign, I'm actually going to have a negative 1, right? Because I actually lost 1. So 5, 6, 7, 8, 9, minus, take away that 1 is 8 valence electrons. All right, that's going to end this one. There'll be another video for the back.